speakers will be talking today about the Bertin technology solutions. So we are 10 years after the Fukushima Daiichi accident, and I would like to invite you today to listen to the presentation from these two speakers about their solutions in the different devices and different measurements what they take and they offer in their frame of the radiation protection. So we have Madaric Manuel, he's head of international sales, nuclear health physics, and Regine Hattab, sales and business development manager. Manuel, I would like to invite you to share your screen.
Yes. Can you see it?
Yes, very well, thank you.
Okay. I don't know if you want. Okay. Okay. Thanks a lot, Emilia, and thanks a lot also to the ENS for the opportunity for Regine and me to present Bertin and also the group CNIM group. And yes, thanks a lot for that. And I would like to start with quick introduction. I don't know, Regine, if you want to also to start your video later. So it's like Emilia said, my name is Manuel Madaric. I'm employed at Bertin GmbH in Germany. And my colleague Regine will speak about the CNIM group later. Regine is also has a degree in mechanical engineering and working for CNIM for over 15 years. About the content, at the beginning, I would like to introduce Bertin and CNIM, the CNIM group. Then the first part would be the CNIM nuclear offer. So this will be presented by my colleague Regine. After, I would like to quickly present the Bertin nuclear offer. Probably for many of you, maybe Bertin and CNIM is not so known as a nuclear supplier or supplier for nuclear in the nuclear field. And then I would like to speak about or to present few case studies, especially because I took this example for environmental radiation monitoring systems 10 years after Fukushima. So make a quick analysis what happened in terms of environmental and radiation monitoring systems during the incident, and what is the evolution, what was the evolution development in the last 10 years. And then for sure we have time for questions and answers. I hope so. So I have to speed up a little bit. Okay.
Just to mention, this meeting is recorded, and yes, if I will moderate the questions. So if you have any questions, please put them in the written mode in the Q&A tab. I will read them to the panelists. Thank you.
Okay. Quickly about Bertin GmbH, you see on the right the picture. This is our subsidiary. So we are a corporate member of ENS, and thank you again for this opportunity to have this webinar. The opportunity. So we are located in Frankfurt am Main in Germany. Founded in 1985. Previous as Janitor Instruments was the name. Here in Frankfurt, we are 26 employees in the nuclear field. We are a few more, but in the nuclear field, we are 26 people. And it's mainly focused on R&D, production, sales and service for environmental radiation monitoring systems, health physics devices, and radon monitoring equipment. Bertin GmbH, we are a subsidiary of Bertin Technologies France, and which is a CNIM group company. To show you a little bit the CNIM group, some key figures you see in the center, and as Emilia said, if you are interested in more details later, you can, as the webinar is recorded, you can have more details on that. Just a few key figures in 2019. Our turnover was about 600 million. CNIM is listed on the stock market in Euronext Paris. We were approximately 2,700 employees in 2019. CNIM is dealing in two main sectors. The first one is called environment and energy. You can imagine the main part CNIM is dealing here. It's for example waste to energy plants, so turnkey solutions to build and engineer waste to energy plants. And the second part is innovation in systems, where you can see where we are also located with the nuclear part. CNIM has a long history, more than 160 years, starting with big industrial projects with submarines and so on. And also you will see later, Regine will show you some nice examples of the projects CNIM is doing on especially also on nuclear field. Then inside CNIM we have the Innovation and Systems Sector Organization, which is CNIM Industrial Systems. For example, this is also the part where what I mentioned that Regine will speak about is the high safety solutions for nuclear industry, and the Bertin part, which is instrumentation for the NPP safety. You can see for CNIM, for this part, the main facility for production is La Seine-sur-Mer in France, but also a few subsidiaries. And for Bertin, we have the headquarter, Bertin Technologies, the headquarter in Montigny, Bretonnier, and subsidiaries in Italy, in US, in Germany, where I'm located, in Sweden, and the UK, and in a few others in France as well. But I will show you in detail later. What is important to say also that we are offering the complete cycle, starting from the research and development, engineering and design, industrialization, manufacturing, test, installation, and site support services, factory support, maintenance, and so on. Just to show our Bertin DNA, we are saying it's 60 years of innovation. Founded in 1956 with maybe all of you know the Aerotrain in France, and so on. And then so you see the innovation. So we have a lot of innovative products, as we are founded as an engineering company. And just to say at the latest, which is quite exciting, is the optical components. Which are used on the Mars mission. So for the rover, the SuperCam was equipped with Bertin's green light optical components. That's very nice, and we are very proud on that, to be a part of this story.
It's very impressive to see how long your story is in this over 60 years expertise. It's really impressive. I would add one date to your line. It's 2006 when Bertin became our corporate member.
Okay. It was 2006. Thank you. Okay. Yes, and especially for this, I would say Mars mission. It's the second. It's also the second project we did with NASA space mission on the Red Planet. Within this system instrumentation, we have several parts. We have the defense and security. It's mainly CBRN detection, so chemical, biological, nuclear, and radiological. Then we have the nuclear and health physics. That's the part we will present today. We have space and big science. It's also very, very exciting and very nice, exciting part of what we are doing. It's, for example, design, manufacture, supply state-of-the-art optical systems. For example, optical components, onboard instrumentation, instrumentation for plasma experiments, spectrographs, optical ground support equipment, high precision components for synchrotron market, image slicers, and so on. So it's a very, very exciting division as well. Then we have life science business. Life science business is products for research and for medical applications. For example, RNA, DNA, homogenizers, and so on. And we have a part it's dealing with medical waste. It's for reduction of volume reduction and biohazard waste. But today we are talking about the nuclear and health physics for sure. Now I would like to give, so this was the introduction. So please feel free later to ask questions. I don't want to spend too much time on it. But just to show you what about the background of us and how we are structured. And now I would like to that Regine take over the.
Okay. Do you hear me yet? Yes.
Yes, we hear you very, very well.
Okay, good. Because I have some problem with the audio at the beginning. Okay, good. Okay. To make it short, are we next slide, please, Manu? Yes. Okay. Thank you very much. To make it short, I will simplify the activity of CNIM by two main activities, two types of nuclear project: advanced nuclear equipment manufacturing and high safety nuclear handling system. I will approach these two types of activities through example in the following slide. Okay, next, Manu. Okay, we start with the manufacturing of the equipment. Okay, next. Before showing the example, some words about our skills from CNIM. CNIM has an efficient industrial facilities to the manufacturing of large-scale components with detailed design, with complex geometry to a very high level of precision, high quality. CNIM skills in boiler making meet the most demanding code and standards of the industry, such as ESPN, pressure part, COFRAC for certification in France, ASME and RCCM code, nuclear code. So CNIM design and produce very high performance assembly in different materials, like aluminium, duplex, Inconel, and we can see on your right, Chernobyl link tightness membrane in polyurethane and in polyurethane, sorry. 18 months of development, 6 months of series manufacturing, over 2 kilometers of membrane manufactured in polyurethane, sorry. Next. So, the next, okay, thank you. On this slide, it's concerned the ITER project. ITER is the biggest machine to deliver fusion energy. CNIM has got a strong involvement in ITER project since 2009. You can see in the top left corner a picture of tokamak, the machine who produce fusion energy, where the radial plates are located, okay? We manufacture 35 ITER radial plate for ITER tokamak. The dimension of this structure, 9 meter by 40 meter, thickness 110 millimeters. High accuracy machining, so 1/10 of millimeters, and specialty from CNIM is the local vacuum electrobeam welding. Okay. Another example in the next slide, thank you. Another example of nuclear equipment manufacturing, also for ITER project, is a divertor cassette body. This equipment is supporting the plasma components of the divertor system is a vacuum vessel. Of course, you can see also the located of the bottom of the tokamak. This equipment is resistant to intense heat flow from 10 to 20 megawatt square meters. This equipment is made of tungsten, the metal with highest melting pot. Okay, another example, next slide. Alors, this project is RGH, of course, is Jules Horowitz reactor. The RGH is a research reactor in Europe for the study of the behavior of nuclear material and fuel under irradiation. The reactor vessel is a ESPN, nuclear pressure equipment, level 1, important element for safety. So, In this slide, you can see a large complex equipment under nuclear pressure. The standard and the code are SCCM and ESPN. The dimension 8-meter height, 0.7 meter for diameter, and the weight 20 tons. Very high accuracy machining and assembly, and from CNIM, electrobeam welding of aluminum. Okay, so now the second type of activity from CNIM is high safety nuclear handling solution. So next slide. Hi. Okay. CNIM provides turnkey handling system from design to on-site installation. So we can see CNIM propose different design solutions, complex electromechanical structures under irradiation, full control command, dry and wet nuclear fuel handling. And that is important, reliability and risk analysis, seismic problem, for example. Okay. Handling products are in compliance with nuclear code, like COFRAC in France, ASME, RCCM, and international nuclear safety compliance. Of course, as I said, turnkey delivery, manufacturing, and FAT, factoring acceptance test, on-site delivery, and integration maintenance. So, example of this handling system, the first example, next slide, it's about a project for Areva. Of course, the client was Areva, now called Orano in France. The project was GB2. GB is for George Best 2 for the uranium enrichment plant. Sorry. So we can see a transfer trolley with a semi-automatic remote control handling system. CNIM added value concerning this manufacturing, this handling system was European directive, Areva standard at this period, nuclear environment, ability to withstand earthquake, insurance, the integrity of the uranium container, high degree of safety and reliability, and of course high accuracy, 1 millimeters. Okay, next example. Next slide, Manu, please. Alors, this product, handling product, how can I say, is a flagship product from CNIM Nuclear. CNIM has been manufacturing the SFCTF. Alors, SFCTF means Spain Fuel Cask Transfer Facility since 1980, the beginning of the construction of nuclear power plant in France. This SFCTS is in service in 16 French nuclear power plants and is in ongoing delivery for 3 international RPR units. Taishan in China, OL3 in Finland, and HPC Hinkley Point in England. So the SFCTS is a system used to transfer spent fuel from the storage pool into a safe container and then transfer the container out of the fuel building. This product is fully automated procedure to ensure complete safety. Globally recognized for its performances, efficiency, and durability. The dimension of this equipment is 6 meter by 6 meter by 4 meter. The weight is 80 tons. Material is stainless steel. Okay. Another example is a project, yes, from Posiva. Posiva is a joint venture between Finnish electricity company TVO and Fortum. We have contractor to produce a critical package handling for geological storage. We design and manufacture remotely operated spent fuel handling and transferring machine for a Posiva encapsulation plant. Those equipment are compliant with the Finnish Nuclear Safety Authority. Very high requirement to be met, including seismic calculation and handling experting in a radioactive environment. And you can see the picture is a cask transfer trolley. Is a handling system, is a specialty of CNIM. For the conclusion, what I can say is backed for its long experience with nuclear projects, CNIM takes up your challenge by providing innovative solutions, meeting the requirement of the most difficult environments. Thank you for listening.
Thank you very much, Regine, for these nice examples and the presentation. I'm sure there will be some questions later.
Yeah,
I hope so. So thanks, Ayas, and we continue with the second part, which is the sorry, I'm in the wrong. Which is the Bertin nuclear offer. So what Bertin is doing as a nuclear offer is for sure different than CNIM's part, than Regine, what Regine presented. So our main nuclear part is detection and measurement of ionization and radiation. What we are doing in detail. From our long experience, we are doing consulting, engineering, and feasibility studies for our clients. Providing equipment for health physics or health physics devices, how we call it. One very important part is environmental radiation monitoring. It's also the cases I would like later to present, especially after Fukushima accident. So environmental radiation monitoring systems, we call it ERMS. Then radiation portal monitors. It's also so our main clients are is the nuclear market, so for pedestrians and so on. Then we have a part which we are calling technologies and systems on demand. I will show you later once a quick slide what does it mean, but you see it's something very special. Radon monitoring and measurement. I have no specific slide on that. It's radon. Probably everybody knows from you. It's a natural gas, so it's not directly linked with nuclear, but it is at the end, because you can imagine measuring artificial radiation, also for nuclear facilities, nuclear power plants, and so on. Means you want to detect as much as low as possible the artificial part. The problem often is that the natural radioactivity coming from radon, for example, radon or thoron or the radon progenies, it's much higher than the artificial part you want to measure. So therefore, radon monitoring is also used in nuclear facilities to determine the natural part. To compensate or to be sure that for example, the detected radioactivity is not coming from the artificial, but it's coming, for example, false alarms, rate investigation, and so on. But it's coming from the natural gas. So we have also many clients from nuclear field using our radon monitoring equipment, even if it's natural gas. And for sure, very important for us, it's also services and calibration. Here I also do not have a specific slide, but we are offering on-site services, also factory services, calibration, and so on. Just to give you a quick overview about the health physics devices, because it's also linked to nuclear, or nuclear is our main market for this. So dosimetry systems, for example, including teledosimetry systems. So we have here, we can say as our main references, for sure, it's EDF in France, where we have more than 25,000 dosimeters in operation, including the maintenance of the systems. Then air monitors, for example, like the portable systems for aerosol monitoring, for workplace monitoring inside nuclear facilities, for example. Contamination monitors with alpha beta detectors for to measure the contamination on surfaces. Here also we have with this product, for example, EDF is one of our main clients. And then a dose rate and Sauvy meters, so small meters, Sauvy meters to determine the dose and dose rate. Then radiation portal monitors, or we say access control. And just a quick slide about that. So we have what we are offering. It's for pedestrians and low volume sample control. You'll see it here. For example, this is a gamma whole body monitor on the entrance of the French nuclear power plants. On EDF sites in France, I think we cover 90% of this entry and exit gamma monitors, and approximately 90% of the vehicles. So, for example, here you can see detectors for the entrance or exit for vehicles, cars, trucks, or trains, or small containers, and so on. Could be for gamma, it could be for gamma neutron, for sure. Usually for the nuclear power plants, for the nuclear market, mainly gamma is interesting, but especially thinking on Swedish nuclear power plants, they're using gamma neutron systems on the entrance for pedestrians, as well also for the vehicles. And then technologies, systems on demand. What is behind that? It's in fact, it's systems designed and adapted to customer needs. You saw already this picture at the beginning. It's a small tractor. It's like a grass cutting tractor. It's one of the projects where we designed this truck with a big, large contamination monitor at the bottom. So it means it was also for several nuclear power plants, so that big surfaces can be checked for contamination. It's a 1,200 square centimeters detector. It could be equipped also with a guard detector, so for high gamma background, for dynamic compensation, and so you can control big areas with this. Outside, for example, around on site with this tractor, and this is something you cannot buy. This is not a standard product, so we have been designing this for on special customer needs. As well, for example, special radiation monitoring systems, type approved, classified. Here you can see it's online gas monitor or liquid monitor. It could be both, which is really inline measurement with a safety classified electronics. Then we are designing specific laundry monitors for our clients. Here you can see an alpha beta laundry monitor. It's a horizontal one. We have a vertical one. It could be alpha, beta. It could be gamma, and so on. So specific design on customer requirements. Or here you can see specific clearance monitors. You see with this big long conveyor. It was designed for these scaffolds parts which are long. So we designed this clearance monitor. It's also gamma detectors to measure these long parts after used in the containment of the reactor. It was a mobile system after to be placed when the parts are not used anymore from the containment. Then one slide about the measurement on environmental radiation. What we're offering, it's gamma dose rate stations, so probes like you can see here on the picture. Then spectroscopic ones, which are more and more used. You will see later when we come to these cases. air monitoring stations. So for example, for aerosols, noble gas, and so on. And then for sure the data management for all of this. And what Bertin is offering is, and especially the Bertin GmbH, is this entire turnkey network solutions. It means from the single sensor up to the entire turnkey solution. Yes, you can see here, but this will later. I will speak about that, about the seismic approval, for example. Now I would like, especially coming back on this environmental, because I think this is the first of all, we are specialists on this field in ERMS systems, and second, I think it's the best where we can see the evolution after Fukushima in the field of radiation measurement. So environmental radiation monitoring systems 10 years after Fukushima, few case studies. First, I would like to point out the main identified weak points during and after the Fukushima incident, or how we call it. This is a summary of what have been seen during the event, and also what was I would say the result after all the stress tests and the authority tests we saw worldwide after the event. So it's a combination. What we saw during the event was that partially there was no data, or the stations didn't provide reliable data. For sure, also some stations were out of order during the event. We know there were issues with power supply. We know there were issues with data communication, issues with the measurement range, general design issues, some seismic flooding for sure. Not enough measurement points, so the mesh was not tight enough, let's say like that. And for sure, mainly simple dose rate online measurement systems were used before. So this is what we can say, very general. What we can say. After the event, what we could see is the main improvements, and what Bertin is offering, in fact, since many decades, is intelligent probes and sensors, also designed, and very important, designed for the emergency conditions. Also new measurement techniques, for example, spectroscopic, at least to have it partially in a system. Why? Maybe you can remember when the results have been published during the accident at Fukushima, was that some of the events showed in the diagrams. It was not clear what was the cause by it. For sure, for few high, for example, dose rate values, it was clear it was the noble gas, but for few of them, for few peaks, it was still not clear what was the cause of it. So with the spectroscopic and the nuclide identification, there's also the possibility to identify the nuclides. For sure, in uninterruptible and alternative power supply solutions. Very important today is also redundancy and emergency-proof data communication. You will see a few examples later. Wide measurement range. It means the system should be able to be very sensitive for the routine measurement, so very low minimum detectable activities, but as well with very high end range to be also able to be used for the emergency with the same systems. And for sure, the systems must be designed for harsh environmental conditions. So Bertin is offering the seismic tested, seismic approved systems, IP68. So also you can place them underwater, wide temperature range, and so on. For sure, also the increase of number, but this is also what we see in general, that since the event after the stress test, the number of I say stations, I mean probe sensors, you can, yeah, it's the same word here, is increasing after the event, and also complement with quick deployable units. So in case of an emergency case, that with deployment units, you can tighten the measurement. And what we can say, Bertin has more than 40 years experience in ERMS, And we have more than 4,500 sensors operating worldwide in more than 40 countries. Already with all these features. Even for sure, few came after Fukushima, but many were already available also before. The first case study I would like to show you, it's not from Europe, but it's a very nice one. So because it's very impressive, it's the Bruce Power nuclear power plant in Canada. It was a very a nice project for us, and I think it's very impressive especially to show you what I've discussed before. For sure, after Fukushima, there was a CNSC recommendation, sort of from the Canadian Nuclear Safety Commission. It was the recommendation 5C. So you to check the existing I would say, let's say, boundary radiation monitoring systems, to check for several things like backup power and so on and so on. In addition, for example, Bruce Power, who is the operator of the plant, with their safety culture for continuous safety improvement. And at this time, it was in 2011. They checked the existing emergency radiological surveillance system for possible improvements, and for sure there was a lack of a lot of improvements. So Bertin was contracted in 2012, sorry, to design, deliver, to do the installation and maintenance and training for entire environmental radiation monitoring systems. You see on there's a nice picture of Bruce A and Bruce B of the 8 kind of reactors. Impressive nuclear power plant with I think it's more than 4,000 employees on site, and it's the biggest energy supplier in Ontario, and for sure one of the biggest in the world, but the biggest in Canada and in Ontario. I think they are making more than 30% of the power in Ontario. What was the scope of the basic system? It was 49 stationary systems, spectroscopic systems. So in this case, all systems were spectroscopic. Partially also we've included meteorological stations to have the wind speed, wind direction, rain, and so on. In addition, they have 10 quick deployable spectroscopic systems and 8 integrated radiation monitoring systems, so air monitors. All systems for sure, as I explained before, with a wide measurement range. The data transmission in this case was again, it was the standard one is GSM 4G. For sure, this is not an emergency proof, but it's for the routine operation that all the systems are transmitting the data through the cellular network. So all systems have an integrated SIM card, and they are transmitting through the cellular, because this is cheap, and if there's no emergency, there is no issue with that. In case of an emergency, and in case of shutdown, of for example of the network, of the cellular network, the probes automatically switch to satellite. In this case, it was a global star satellite provider. So inside the probes, there is the modem included. So the systems automatically switch to satellite and transmit then through the satellite emergency proofed data transmission. Was very important here. For sure, very harsh environmental conditions. You will see a few pictures later. We have very large temperature gradients, especially in autumn and in spring, where you can have very cold nights. But then in the morning it could be, so the gradients are quite high, and also the wide temperature range. You can imagine the cold winters. Also seismic approval was very important. For sure, also the power supply. So all the spectroscopic systems are working 24/7 with battery backup and solar supply. Here just a quick overview, a sketch about the data communication and data flow, where the probes are the cellular and the global star satellite network. How it's just to have offended. This is maybe interesting to show also the layout, what we at the end defined with the client. You can see here it's the Lake Huron, and you have here the site. And in fact, there's like let's say it's like a perimeter monitoring. So the 16 stations are around on the area of the nuclear power plant. We have offsite 33 stations, which are also divided by let's say a boundary here and far here. So it's up to, I would say it's it could be some 10, 15 kilometers, I would say, is the, or maybe more, I don't remember. And in fact, it looks like random, but in fact the gap is maximal 3 degree. It means that all the stations are located that you have the 3 degree maximum distance of 3 degree. So in case of an emergency or in case of a cloud, the maximum distance between the one and the other probe is 3 degree. This was the when we did the planning. Here you can see a few pictures. This is nice weather picture, and you see the probe, you see the solar panels. This is the battery compartment. It's a special pole with a special fundament. One question could be for sure the international recommendations saying, okay, the height of the center probe should be at 1 meter height. Theoretically, this is correct, and this should be followed, but you will see later why this is, for example, here not possible. And with these solar panels, it's a 24/7 operation. They are quite high. Even we are using ultra low power systems. But in winter time, you have several months without sun, with a lot of snow, and so on and so on. So this has to be considered. We are considering, and also you see the angle of the solar panels are quite high. So it's designed for the winter conditions. Also, what we are using here inside, so you see some other pictures. Inside, we are using a special lithium battery. A special lithium battery, which has still a capacity of approximately 80%, even at -30 degree. So this was also very important. You cannot use a lead acid battery in this case. You need a special battery. You see here, for example, it's also this is the meteor station, or Vaisala meteor station, which is directly connected. Here you see the satellite antenna. This is the 4G cellular antenna. As we are sometimes here in the nowhere, sometimes there is no for plenty of kilometers there is no village. So also the 4G coverage is sometimes not that good. So that's the reason why there were external antennas were required at this time. Then, as I said, just complement to these 49 stations, they had also these mobile ones, which are stored in such cases and stored in the emergency facilities with the emergency trucks, so which could be brought out in case of emergency. And you see some pictures where we did some we put. So in fact, they are also used in routine operation. They bring them out just to be in operation. Then the air monitoring stations, and just to show you a few quick pictures. So you see, it's in fact it's a outdoor special outdoor enclosure, and here you can see one picture of the inside with the yellow, the special batteries. So they are, as I said, there are few of them are equipped with emergency power backup. It's tricky. You can imagine that each aerosol air monitor needs you're sucking air through a filter, so you need a pump. Each pump needs some power, and to reach low minimum detectable activity, so to be sensitive, you need a bigger pump, because the flow rate is going proportional to your minimum detectable activity. So here you have double the flow rate. You have double half less the minimum detectable activity. So it's an issue. And in this case, we are using a special pump, a special low pump, a power pump with 90 watts. And therefore we can use these batteries. It's I think 1000 ampere hours at 24 volts DC. which can operate for 4 to 5 days. And with a special designed algorithm, our physicists did, we can even reach very low minimum detectabilities. And you see there was also the foundation for the concrete. It was also designed for the seismic and so on. And there's a special hut on it for the snow coverage and so on. Then the data management system, I just show you a few pictures. So they can it's a web browser based, so they can the client can zoom in, click on the value and see immediately the graphs. They also other systems are integrated in. It's for sure usable also on mobile systems. And even if you click on a result, you are receiving the spectral analysis, so you know what it is. And already they had these issues that sometimes they had alarming of not only of these systems but also of the portal monitors and so on. And then they could recognize through the environmental monitoring system that it came from natural radon progenies. And yeah, you see here why it's it is needed to have the height of the system's design. You see that there's a lot of snow in winter. It's beautiful in summer, but it's also beautiful in winter, but very strong winter. And that's the reason that the height was designed to these 3 meters. Okay, this was the one of the case studies. I hope it was interesting. Another quick one, just because it's a different. I will speed up a little bit now, but more to show pictures. It was for the EDF in France. It's for in fact, to give you some background, EDF is using already our environmental monitoring systems for each nuclear power plant. So they have the probes around the nuclear power plant sending through radio link to a receiver. This is the fixed standard environmental monitoring systems. After Fukushima, they also wanted to improve, and what they did is they wanted approximately 164. I think what we delivered. It's you see of this special quick deployment dose rate probes. So really for quick deployment in case of emergency. So they are stored centralized, and they share out in case of an emergency case in IDDF. And then they have this dashboard and where they can see where the probes are located. There's a GPS inside and so on. And they also shared or spread with the farm emergency vehicles. I show you one quick video how this works. So it means you have your probes in the storage and the transport case. You go out in case of emergency. You take them out. You just activate them from outside with a magnetic read contact. It's a thing of 1 second. And then what you can do, just to show you this video. So you can bring out the probes in seconds. It's this is also one of the I would say results after the Fukushima stress test is that more and more these quick deployable emergency measurement channels are established. They have only one slide about this. It was Dukovany and Temelin nuclear power plant. Unfortunately, I don't have pictures, or I don't have pictures I'm allowed to show, but just to show you how does it work. So there are probes around nuclear power plants. So on Temelin and Dukovany, which are both operated by ČEZ. Each nuclear power plant has a seismic proofed Skylink proprietary radio receiver. So Skylink is a radio technology developed by Bertin. So it's proprietary. So it's owned by the operators. So it's emergency proofed. And in this case, the probes are sending the data automatically to the receivers. It's redundant, and they have also receivers mobile in case of really super GAU. They want to drive with a car around. So you see it's consisting of 64 probes, which are partially also equipped with meteor stations. It's also for fixed, deployable, and portable, and all are sending the data through this proprietary radio data transmission link. Everything was seismic tested according to the spectra we received from the buildings, depending on for sure where the equipment is installed and so on. Yes, this is also one slide about Kirschko NPP Slovenia. You see the here dose rate probe, also with radio link, also with the seismic designed concrete. For sure, this probe has a weight of 2 or 3 kilograms, and if you see the concrete and how deep is it and so on, so you see the design of the. So it was equipped of such dose rates. It's perimeter monitoring on the site on nuclear power plant, and then also here aerosol air monitors, which are also, and all the systems are sending the data also through this proprietary radio link. This is the solution which we are delivered, I would say, for many nuclear power plants, because this radio link works up to 10 kilometers. So the simple one up to 10 kilometers, the high end one up to 50, 60, up to 100 kilometers. And they are also using this inside the control area. You see they installed also probes inside the area. What I would like to show you here is only what is important if you design such a radio system. It's that at the beginning you made a simulation. So you put now it's very nice because we can put the simulation into Google Earth. You put the location, and then you can put your probes, and then you see, for example, the red area is the good reception of the probes. No? So if they want to install them fixed, this is a very large scale, but in fact, you can what we can do is we can simulate the radio reception before we install them to be sure that the system will work and that the data will be transmitted reliable. Then yeah, for sure, then there's a data management systems where they have the picture, and around they have the data of the probes, and they have the nuclear alarm or technical alarm and so on and so on. Then also what I said before, these quick deployment units. For example, this is a case study for Ningxie, Hongzhou, and Taishan. Several nuclear power plants in China, where have also a dose rate probe with some meteor wind speed and wind direction, which are also stored in special cases and which are only used for emergency as well. Also with radio transmission. And then just as one of the last slides to show here in this case, I'm also not allowed to speak about the client, but all these systems exist as quick deployment units. You see here, for example, air monitors, which are integrated air monitors for aerosols, dose rate, and so on, which are here on an open trailer with a diesel generator, or here on a closed trailer, which everything is fixed, installed, the closed trailer with AC and so on, also with a diesel generator. Or here, as I showed you before, the spider probe with the quick deployment, or here's another probe which is called gamma tracer for routine operation and emergency, but with yes, other possibilities of data transmission. And for sure, what is more and more also complementary is on the water side monitoring on buyos, where we can provide. This is, for example, a design where we have a probe on top of the buoy, on one probe, a spectroscopic probe in water, also solar supply, transmitting the data, and so on. And what is also important to say, all these systems are intelligent. So even if the data communication is out of operation, for the probes are intelligent, saving all the data, and when the data communication comes back, it's transmitting the data through satellite, as I said, through satellite, through radio link, through cellular or some others we are offering. This is also to show you a few references especially for NPP monitoring, so for nuclear power plant monitoring. So if you're interested to read that later, or and you see the picture on the right, it's in Borsele, a nuclear power plant in Netherlands. It's also an installation on a height, because mainly on floating. Floating was there. Floating and seismic was a high requirement there. Why it's the height so high, and you see the concrete, which was especially done for this installation. So what you can say in general is that the environmental radiation monitoring systems change a lot in terms of requirements on seismic, data transmission, power supply, and so on, which was not before in these dimensions done. Some further references, but this is more on early warning networks. Some countries, so they have different philosophies on environmental monitoring systems. Sometimes the nuclear power plants are responsible. Sometimes it's the countries, the states. So it's depending on country and how it works. Yes, last slide. I think it's more general. What also Regine already mentioned before. Our memberships. So we are in different international memberships. Our certifications for sure, ISO 9001 and so on and so on. Our nuclear quality certifications, like COFRAC, already mentioned by Regine as well. Our main references. And yes, I think I'm late, but I hope I was not too late and not too quick, and yes, and not too boring.
No,
thank you very much.
Thank you very much, Manuel. Thank you very much, Regine. It was very informative. I learned also myself a lot.